Hi students, in this video we're going to cover the dot product. There are two versions of the dot product and we're going to connect the two to help us solve some sorts of problems. So the first version of the dot product is for two vectors we have in R3, meaning that we're going to have two vectors each with three components. So even though we're dealing in R3, we're going to just draw the vectors in R2. So say we have a vector u here, and then we have another vector v, and the head of the vector has the components u1, u2, u3, and the same for v, where we have components v1, v2, and v3. It stops at that point out in space. So the first thing that we get with the dot product is the dot product is the sums of the products of the matching components. So, like generally we'll say that the first component is the x component, the second component is the y component, and the third component is the z component for both variables, for both our vectors, I'm sorry. So if we multiply the x's, multiply the y's, and multiply the z's and add them together, we get this dot product. So an easy example is, say we have u equals the vector 1, 2, 3, and v equals the vector 4, we'll say -5 so the number doesn't get too large, and 6. So our dot product u times v is going to be 1 times 4 plus 2 times -5 plus 3 times 6. So that's just 4 minus 10 plus 18, which is going to be, what's that, 22 minus 10, so 12. Our dot product would be 12. So that's one version of the dot product. This, being able to get a single value from this is helpful, because in the second version of the dot product, we have the dot product is the magnitude of u times the magnitude of v times the cosine of the angle between the two vectors. Now, generally, we're not going to know theta, but since we have another version of the dot product, we can fill in this part I'm circling, the u times v part, and since we will always be able to find the magnitude of the two vectors if we have their components, then we can manipulate our formula to get u times v divided by the magnitude of u times the magnitude of v, and that's the cosine. And remember, in the numerator, that corresponds to this value of 12 that we were able to get by using this version of the dot product. And so, of course, once we know the cosine value, we can apply a cosine inverse to both sides, and we get that theta is actually the cosine inverse of that value. And so connected, this is what we're really using. We found this in that first example. We'll always be given the magnitude, and that allows us to solve for this. And so that's what we'll do in a couple of examples. So for our first example, we have two vectors in R2, and we want to find the angle between the two of them. So first, we can calculate our dot product straight out. So we'll have u times v, that is equal to, that's going to be 2 times 7 plus 3 times -1. So that is 11. We know the magnitude of u is going to be, remember, when the vector is given in component form, the magnitude of the vector is the square root of the sum of the squares of each component. So that's going to be the square root of 13, and then the magnitude of v is going to be the square root of 7 squared plus -1 squared, which is the square root of 50. So what we know is All right, so our dot product u times v equals the magnitude of u times the magnitude of v times cosine theta. So we know u times v, that was 11, the scalar product. So 11 equals the square root of 13 times the square root of 50 times cosine theta. We want to find theta. So 11 divided by the square root of 13 times the square root of 50 equals cosine theta. So cosine inverse of that value, root 13, root 50, is going to equal theta. So I'm going to move over to Desmos so we can actually calculate that. It was 11, 13, and 50. So we're going to go to functions. We have cosine inverse. If you're using Desmos with me, make sure you're in degree mode. So we're going to have cosine inverse, and I believe it was 11 divided by the square root of 13 times the square root of 50. And that's going to give us 64.4 degrees. So 64.4 degrees equals theta. And so now for part B, we're doing the same thing, but we're in R3. So even in R3, the vectors can kind of look like they're in two dimensions because one vector is going to be in some way above or on top of the other. So the concept of an angle between the two vectors still makes sense even in three dimensions. So the first thing is we have this in unit vector form because we have 3 times the unit vector for I, 4 times the unit vector for j, and 5 times the unit vector for k. So that really means that just u is 3, 4, 5, and v is 4, -2, -4. So first, our dot product that we can calculate by just multiplying the components is going to be 3 times 4 plus 4 times -2. Make that a lot. 4 times, we'll put that in parentheses. So 4 times -2 plus 5 times -4. And so that's 12 minus 8 minus 20. So it's -28 plus 12, which is -16. Okay. And then the magnitude of u, so we'll say the magnitude of u is equal to the square root of 3 squared plus 4 squared plus 5 squared. So that's 9 plus 16 plus 25. That's going to be the square root of 50. And the magnitude of v is going to be the square root of 4 squared plus -2 squared plus -4 squared. So that's 16 plus 16 plus 4. That seems like the square root of 36, which is 6. So what we know is theta is going to be cosine inverse of -16 divided by the square root of 50 times 6. So we'll go back over to Desmos. So we had cosine inverse of -16 divided by the square root of 50. And this time we had a 6 instead. So that is 112.2 degrees. So theta equals 112.2 degrees. You do see, pause the video, come back and see if you can get the answer. So if you're rejoining me, we will get u times v by multiplying the components is 5 times -1 plus 1 times -3 plus 4 times 2. So that's -5 minus 3 plus 8. That seems as if we might get 0. So imagine we didn't get 0 for a minute. Then the magnitude of u is going to be the square root of 5 squared plus 1 squared plus 4 squared. So that's 25 plus 16, 41 plus 1. So we get the square root of 42. And the magnitude of V is negative 1 squared plus negative 3 squared plus 2 squared. So what's that, 10 plus 4? So the square root of 14. So 0 divided by the square root of 42 times the square root of 14, cosine inverse of that value is going to equal our theta. So we should know that the cosine of pi over 2 or 90 degrees is 0. So this is going to give us pi over 2 or 90 degrees. So if it turns out that the dot product is 0, and that's going to imply that the angle that we get between the two vectors is 90 degrees, we have reached something useful, that when u times v equals 0, u and v are perpendicular. So there's another word that we use for perpendicular in Cal 3 and just moving forward in like R3. And that word is orthogonal. And so it actually comes up right now. So two vectors are orthogonal if the angle between the two is 90 degrees. And that's going to correspond to the dot product being 0 because the cosine of pi over 2 is 0. So for this example, we're trying to determine which two vectors are orthogonal. So all we need to do is pair them up, do the dot products. Whichever one gives us 0 is going to give us a pair of orthogonal vectors. So the product u times v, we might be quick at doing this now. So that's going to be 1 times 3 plus 2 times 0 plus 3 times negative 1. Now it's going to be clear. Well, let's see. We get 3 plus 0 minus 3. So that's 0. So u and v are orthogonal. Tricky word to spell. Orthogonal. If we check u times w, that's going to give us 1 times 7 plus 2 times negative 2 plus 3 times negative 1. And that's going to equal 7 minus 4 minus 3, which is also 0. So u and w are also orthogonal. So now I wonder if, because u and v are orthogonal and u and w are orthogonal, does it mean that v and w have to be orthogonal? Let's find out. So v times w is going to be 3 times 7 plus 0 times negative 2 plus negative 1 times negative 1, and that's clearly not 0. It's actually 22. So just because one vector is orthogonal to two other vectors, we can't like use that transitive property thing where if A equals B and B equals C, then B equals C. So all we know is that U is orthogonal to V and U is also orthogonal to W, but that does not guarantee that V and W have to be orthogonal to each other. And so that's it for orthogonal vectors. It's just two vectors where the dot product is 0, which means that the angle is between the angle between the two is 90 degrees. And so the last thing we want to talk about is an orthogonal projection. So if u and v aren't orthogonal vectors, meaning one's not perpendicular to the other, then we can project one vector onto the other. Now, what that means is like we have this like flashlight example, right? So if U and V were perpendicular like this, if you shine a flashlight straight down, like imagine, actually we'll draw it here. So imagine the light is shining straight down onto the vertical vector. Then the vertical vector isn't going to cast a shadow on the vector that is horizontal. But anytime the vectors aren't perpendicular to each other, one vector has to be, we'll say, kind of like on top of the other. And so if you were to like, we'll again conceptually imagine shining a light down from the viewpoint of the vector that's on top, then that vector is going to cast a shadow onto the other vector. And this is what we call an orthogonal projection, is because the view is, we're going to say, like perpendicular. A way to think of this is how much of the vector that we are casting a light on, how much of it is on the horizontal vector. In this case, like how much of vector u is on vector v. And another way to think about that is if you were to write u in terms of v, meaning that like v is our basis vector or our unit vector, what would it look like? And so the formula that we have for this, and we can derive it in class, for the video is going to be too long. All right, so we call this an orthogonal projection. And so the orthogonal projection of u onto vector v has this formula right here. So we already know how to find the unit vector. The unit vector is you take the vector v divided by its magnitude. This u cosine theta part is how we're going to say standardize u in terms of v. Whatever value we get, we multiply by the unit vector for v, and that's going to tell us where u is in terms of v. When this part that I have in the curly brace is called the scale of u. It's how much of u, how much u is relative to v. When the value is positive, it's going to mean that u is moving in the same direction as v, like we see in this B diagram right here. And then when the scale is negative, u is just going the opposite direction of v. All right. So we want to find the orthogonal projection of u onto v if u is 1, 4 and v is 2, 7. So all we have to do is stick to our formula. So the projection of u onto v is equal to the magnitude of u. So the magnitude of u is clearly the square root of 17. It's the square root of 1 squared plus 4 squared. So that's going to be the square root. Why am I putting it in absolute value bars? We already have it. It's the square root of 17. And then we have to find the cosine. We have to find theta. Well, actually, we just need to find cosine theta. So remember, we could do this here. We'll get more room. So cosine theta is going to be the dot product divided by the magnitude of the two vectors. So, all right, so our dot product is going to be 1 times 2 plus 4 times 7. So that's going to be 30. And so we're going to have 30 divided by the square root of 17 and multiplied by, let's see, 49 plus 4 square root of 53. So let's go back over to Desmos for a moment. Well, actually, we don't need that. We can just, what am I saying? Oh, excuse me for a moment. We don't need to actually put that into the calculator. We already have it. So that's going to be 30 divided by the square root of 17 times the square root of 53. I'm so used to having to do the cosine inverse. My bad. And so then the magnitude of v we already know to be square root 53. So divided by square root 53, and v itself is the vector 2, 7. So if we simplify, if we clean up a bunch of stuff, the square root of 17s are going to cancel. The square root of 53 times the square root of 53 is going to be 53. So we end up with the value of 30 over 53 times the vector 7. And this is the projection of vector u onto v. We'll talk more about this in class and how we probably can simplify this formula. Simplify this formula into something more useful that's slightly shorter. But that's the video, kids. See you in class.